Hello friends, today we are going to discuss the topic types of gemstones and introduction. The limited availability and significant cost of high quality natural gemstones means that their potential use for other applications such as in advanced technology is also restricted. Thus, by taking advantage of current knowledge of crystal growth methods, efforts have been made by material scientists to produce a number of synthetic gem materials in the laboratory for industrial and jewelry uses. A synthetic gemstone is identical to a natural gemstone in almost every way. This includes the same basic crystal structure, refractive index, specific gravity, chemical composition, colors, and other characteristics. Since the same gemological tests are used for stone identification on both natural and synthetic gems, a variety of methods are currently used in the production of synthetic crystals, resulting in different qualities, appearance, and prices. The limited availability and significant cost of high quality natural gemstones means that their potential use for other applications such as in advanced technology is also restricted. Thus, by taking advantage of current knowledge of crystal growth methods, efforts have been made by material scientists to produce a number of synthetic gem materials in the laboratory for industrial and jewelry uses. This episode gives an overview on some vital types of gemstones and primarily focuses on synthetic gemstones, isotropic gems, biaxial gems, organic and miscellaneous gems. Gems have been objects of desire and admiration in almost all cultures throughout human history. Natural gemstones such as diamond, ruby, emerald, sapphire, and pearl have long had significant monetary value. They and other gemstones have achieved this status by possessing the desirable attributes of beauty, rarity, durability, portability, as well as the transient appeal of fashion at certain times and places. These attributes have contributed to the popularity of gemstones that has continued since ancient times. Necessity. Natural gemstones are rare and highly valuable elements from the earth. Consumers admire the beauty of genuine stones, especially in jewelry, but cannot always afford these pieces. The limited availability and significant cost of high quality natural gemstones means that their potential use for other applications such as in advanced technology is also restricted. Thus, by taking advantage of current knowledge of crystal growth methods, efforts have been made by material scientists to produce a number of synthetic gem materials in the laboratory for industrial and jewelry use. What are synthetic gemstones? Synthetic gemstones are laboratory created versions of genuine crystals with the same chemical, physical, and optical properties. Technicians isolate the conditions of nature and speed up these processes using heat, pressure, and solutions to create synthetic gemstones. Chemically speaking, these stones are equal to genuine gems except that they are made in labs using sophisticated technologies. Due to the controlled environment, synthetic gemstones contain fewer inclusions or flaws than natural gems and feature brighter colors. Common examples of synthetics include the ruby, sapphire, emerald, garnet, and diamond. There are three major methods used today to make synthetic gem minerals commercially. In the first, the flame fusion process, powdered oxide are melted in a furnace by a high temperature flume and accumulated in hardened form as cooling and crystallization take place. By this technique, corundum and a number of other gem minerals are made, including rutile, strontium titanate, and spinel, as well as the non-gem minerals cadmium tungstate and calcium tungstate, which is also called synthetic scheelite. But the second method, a hydrothermal process, quartz, opal, beryl, corundum and fluorite are crystallized from solution under conditions of higher temperature and pressure by dissolving fragments of the mineral and redepositing it as transparent gem quality crystals. In laboratory experiments, most of the important gem minerals have been produced by crystallization from solution. However, only those mentioned above are produced on a commercial scale. The third method is termed flux growth, and this is a means by which, under high temperature and pressure conditions, materials are dissolved in a melt in which they are more readily soluble than in water. In addition to these three methods described earlier, there are several others that are used, experimentally at least, for mineral synthesis. One would be the formation of minerals by direct passage from vapor to a solid state without first becoming a liquid, called vapor growth or deposition. Another method that could be used, and one that may be used in the figure for some types of gem synthesis, is the precipitation of a substance from the solution, in which it is dissolved by setting it free with chemical action. In other words, two or more chemicals are dissolved and a new material is formed by chemical action of ions of the dissolved materials. Diamond synthesis. The fact that diamond is composed out of almost pure carbon was discovered in the 18th century. It was not until the first discovery of diamonds in modern times that our understanding began to develop about the formation history of a diamond. It requires extreme conditions, high pressure and high temperature, to form a diamond crystal. Because these extreme conditions are very hard to reproduce in a laboratory, it wasn't until the 20th century that the first synthetic diamond was produced. Indeed, it was not until the 1950s before diamonds could be made with a machine in a reproducible manner. There are two general approaches for diamond synthesis. One, high temperature and pressure synthesis, which is also called HPHT. The basic technique used in the large scale synthesis of industrial diamond involves the dissolving of graphite in molten iron, nickel, manganese or cobalt at high temperatures and pressures. In this process, the metal acts as a catalyst to greatly reduce the temperature and pressure necessary to convert the hexagonal atomic structure of graphite into the more tightly bonded cubic structure of diamond. The conversion is effected by applying pressure in the region of 110,000 atmospheres to a prophyllite cartridge containing alternate discs of graphite and the metal catalyst, and at the same time heating this to around 3300 degrees Celsius. At this temperature, the metal discs melt, dissolving the graphite. The temperature is then allowed to fall and the graphite carbon recrystallizes as clusters of tiny synthetic diamonds, the process only taking 2 or 3 minutes. After the solidified metallic mass of the cartridge and its contents is removed from the press, it is crushed and the diamonds are extracted by dissolving away the non-diamond content with acids. Second method of diamond synthesis is CVD diamond synthesis. CVD, or chemical vapor deposition, is an extremely versatile process for creating thin solid films and is a generic term for a group of chemical processes that involve depositing a solid material from a gas or mixture of gases onto a substrate. Besides its application in diamond synthesis, CVD processes are widely used in the fabrication of semiconductor devices and in the manufacture of coatings for wear parts and machine tool components. For example, CVD processes for diamond synthesis can be used for the growth of both single crystal and polycrystalline forms of the material. The actual conditions required for making each type of diamond are very similar. It is the choice of substrate that determines which will grow. For single crystal CVD diamond, the substrate needs to be single crystal diamond, and the new diamond film grows epitaxial, with the deposited film taking on the lattice structure and orientation identical to those of the substrate. For polycrystalline diamond, a non-diamond substrate is used. A variety of materials can be used in this context, primarily silicon, silicon carbide, and a range of carbide forming metals including molybdenum and tungsten. In CVD diamond synthesis, the process generally takes place at below atmospheric pressure, typically between 1 and 200 torr. A torr is a non-SI unit of pressure defined as 760th part of an atmosphere. The starting materials or precursors for diamond synthesis are hydrogen and a hydrocarbon such as methane. Only a tiny amount of hydrocarbon, often between about 1 and 5%, is normally present in the gas mix and provides the source of carbon from which the diamond is formed. Although no major economical breakthrough has so far been realized with the CVD diamond process, specialized applications in the cutting tool industry and in the field of diamond-coated cantilevers for atomic force microscopes have been introduced successfully. Diamond films are also used for protective windows in laser-guided missile systems. All transparent substances can be classified as either isotropic or anisotropic. Isotropic includes amorphous mineraloids and minerals in the isometric crystal system. Light entering isotropic gems moves in all directions with equal velocity, creating only one index of refraction. That is, a single refractive index results when light is considered moving in a wave motion with vibrations in all directions at right angles to the direction of propagation. Amorphous materials, which are glass, opal, amber, which lack a regular internal structure, as well as gemstones belonging to the cubic system like diamond, garnet, spinel, fluorite, etc., are isotropic diamond. Diamonds are formed by nature in the upper mantle of the Earth's crust. The atoms in diamond are equidistant from one another. Diamond is the purest crystalline transparent form of carbon. Garnet. The garnet group includes a group of minerals that have been used since the Bronze Age as gemstones and abrasives. 6 common species of garnet are recognized by their chemical composition. They are pyrope, almandine, spessartine, grossular, varieties of which are hassonite or cinnamon stone, and sevorite, uvarovite, and andradite. The garnets make up 2 solid solution series: pyrope, almandine, spessartite, and uvarovite, grossular, andradite. Gemstones in the orthorhombic monoclinic and triclinic systems have 2 optic axes, neither of which is parallel to any crystal axis, and are termed biaxial. Like uniaxial crystals, biaxial crystals have refractive indices that vary between 2 extremes, but also have a unique intermediate refractive index. Biaxial refractive indices are as follows. The smallest refractive index is given the symbol of A or X. The intermediate refractive index is given the symbol of B or Y. The largest refractive index is given the symbol of G or Z. All biaxial minerals have optical symmetry equivalent to 2/M2/M2/M. But in each of the crystal systems, the optical directions have different correspondence to the crystallographic directions. In orthorhombic crystals, the optical directions correspond to the crystallographic axis, that is, the x direction and its corresponding refractive index A can be either the A, B or C crystallographic axis. The y direction and B can be parallel to either A, B or C, and the z direction or G can be parallel to either A, B or C. In monoclinic crystals, one of the x, that is A, y, that is B, or z, that is G, directions or indices are parallel to the B crystallographic axis, and the other two do not coincide with crystallographic directions. In triclinic crystals, none of the optical directions or indices coincide with crystallographic directions, although in some rare case, one of the indices might coincide with one of the crystallographic directions. Chrysoberyl. Chrysoberyl is an aluminate of beryllium with the formula BeL2O4. Chrysoberyl is the third hardest frequently encountered natural gemstone and lies at 8.5 on the hardness scale between corundum, which is 9, and topaz, which is 8. An interesting feature of its crystals is the cyclic twins called trillings. These twinned crystals have a hexagonal appearance, but are the result of a triplet of twins with each twin oriented at 120 degrees to its neighbors and taking up 120 degrees of the clinic trilling. If only two of the three possible twin orientations are present, a V-shaped twin results. Chrysoberyl is a minor ore of the element beryllium and occurs in granite and granite pegmatites. The chrysoberyl species include a few different gemstones varieties. The most common variety is a transparent to translucent from colored by iron, which typically occurs in shades of yellowish to light green. Jade. The term jade is applied to two different metamorphic rocks that are made up of different silicate minerals. One is nephrite, consists of a microcrystalline interlocking fibrous matrix of the calcium, magnesium, iron-rich amphibole, mineral series termolite and ferroactinolite, whereas jadeite is a sodium and aluminum-rich pyroxene. The gem form of the mineral is a microcrystalline interlocking crystal matrix. The most reliable method of identifying jade from other substances is by testing its specific gravity. A simple test to distinguish jadeite from nephrite is a chime test. Nephrite emits a musical tone when it is struck, whereas jadeite does not. Mostly gemstones are minerals with a crystalline structure. However, some gems are not really gemstones. Rather, their origin is organic. This means that they are formed from biological processes, whether animal or vegetable. The class of organic gems is small, but includes a number of unusual varieties that are important in the gem trade: amber, coral, jet, ivory, and pearl. The organic gemstone can be classified in two distinct groups: fossilized and contemporary. Fossilized organic gemstones. These are stones made of once living tissue that has been changed over the time by natural forces into its current gem quality. Contemporary organic gemstones. These are gems made from once living tissue taken from or left behind by creatures living in our time. Since they do not show the effect of eons of natural forces, some collectors do not consider these true gemstones. For example, pearl, ivory, coral. Amber. Amber is a stone formed from a tree sap, fossilized over thousands of millions of years. Amber is usually clear with a yellowish color. This stone resembles and is named after ambergris, a sweet-smelling secretion of the sperm whale once used in perfume making. Examples of amber containing perfectly preserved insects have been found and are considered very collectible. The most prized pieces contain inclusions of insects, plants, or pyrite. The largest amber deposits in the world are near Kaliningrad, Russia, and there are large reserves in the seabed of the Baltic. Pearl. Pearl, resembling a small marble, is usually associated with the oyster, although it is found in other mollusks as well. At the center of each pearl is a small piece of sand or rock which had found its way into the oyster's shell. Oyster attempts to soften the irritant by cooling it in with calcium compound. Over time, layer by layer, the pearl is formed. While usually white, pink, yellow, and even black, pearls can be found. A cultured pearl is produced when the irritant is inserted into the oyster, which is living in specially created oyster beds. They are generally more uniform in appearance. Natural pearls are found in wild, untended oyster beds and are considered more valuable. Coral. The stone known as coral is actually the skeletal remains of a filter-feeding marine animal. Living in colonies, coral can form huge underwater structures or reefs stretching for miles. The Great Barrier Reef in Australia is over 1,200 miles long. The most valuable coral variety is found in the Mediterranean, the Red Sea, and in the coastal Japan. Coral comes in too many shapes, colors, and textures to describe here. Colors can be bright to dark red, orange pink, pink, white, blue, or black. Raw coral is dull, but when polished, it exhibits an attractive vitreous luster. In this episode, we have studied about the synthetic gemstones and also have covered isotropic gems, biaxial gems, organic and miscellaneous gems. We know now that a synthetic gemstone is identical to a natural gemstone in almost every way. This includes the same basic crystal structure, refractive index, specific gravity, chemical composition, colors, and other characteristics. Since the same gemological tests are used for stone identification on both natural and synthetic gems, a variety of methods are currently used in the production of synthetic crystals, resulting in different qualities, appearance, and prices. We also know mostly gemstones are minerals with a crystalline structure. However, some gems are not really gemstones, but rather their origin is organic, which means that they are formed from biological processes, whether animal or vegetable. Thank you very much.